So today we are going to have the meeting to discuss about the storage pool design. Patrick, do you want to get started?
Yeah, hello. Sorry, my microphone wasn't working. Can you hear me?
Yes, I can.
Okay, thanks. So the next step of what we need to discuss today is, as far as I understand, the last remaining open question for storage capacity tracking. Partly that is about the new API in the CAP, but it's also about the more general question in SIG storage, what it means to have storage classes and storage pools and how they are related. So in my CAP, I currently have the concept of a new object called CSI storage pool. And the idea is that this is some underlying set of storage, might be a set of local disks in an LVM logical volume or physical volume group, something like that, where that is used to create volumes in that space. And therefore, that is the starting point for tracking capacity. In my CAP, the only common attribute of a storage pool is basically its topology. It answers the question, where do we have storage? And the answer is, here's a node selector. Any node matching that node.
Patrick, do you want to share your screen to show the CAP?
Yeah, I can open that. Just a second. So you should see my web browser now, I hope.
Yes, we can see it.
Let me see whether I can jump right out. Let's go to the. So it's really about this CSI storage pool question. I could open the full file if that helps, but it's really about this question here. Let me see whether I can open the file in a separate tab. Sorry, that's now getting a bit confusing, but I'll try to make it quick. Okay, so that's the object, the top level object that in its attributes. Well, actually, I just noticed that the topology is in the status, but so it's really an object that just gets created once by someone, and in its current status it's actually in the status where that storage is available, which nodes have access. And that is what the scheduler then needs to know when deciding whether it can use a certain node. It basically needs to look at the node, it needs to look at the storage class of a volume, and then make a decision whether a certain node has a chance of being usable by a pod when that volume still needs to be created. And that's the criteria where the scheduler then can decide, no, I don't have any available storage for that node, for that storage class. I need to find a different node. The storage class is relevant because it may affect how much capacity there is. That's why we have a second nested structure, basically, where for this particular topology, we have different entries indexed by storage class, and that's the key. Basically, this is, strictly speaking, it's a list, but it's defined as a map, which means that the storage class name must be unique among all entries, and that then is the capacity for this particular combination of storage class and location where storage is available for that class. Now, Michelle had this concern that this is just too complicated.
So
And
can I ask a more meta question about the one-to-one mapping between storage class and the storage pool?
I think there is, yeah, okay. Go ahead, just ask your question and I'll answer.
Yeah, I mean, if it's something you're going to talk about later on, you can just table it. But I just want to at least get my question out there. So if I'm trying to create, let's say there is one disk attached to every node of certain kind, and there is one storage pool, hence, on every node.
Yep.
And I'm trying to create a stateful set where I want each of my persistent volume to go to this attached disk now. And I want to, and there's different kinds of disks. So I want to say that I want, let's say there's an NVMe disk and there is a HDD disk. And hence I want to say I want to go to the NVMEs using my storage class. But this doesn't allow me to do that with stateful sets. Basically, storage pools and stateful sets cannot work together in this model.
So I'll try to answer. My understanding is that there is no one-to-one mapping between storage pools and storage classes. It is basically N to M. For each storage pool, we may have more than one storage class that may be applicable to that pool. My one example is LVM, where we have a bunch of disks in a common pool on one node, and the storage class says, I want replicated data that is stored on more than one disk. Or I want to have striped data, a volume with striped storage. Those both may get provisioned on the same node using the same disks, but the capacity is different and it's a different storage class. My understanding of my understanding of a storage class in Kubernetes is basically a contract between the cluster administrator who creates those classes and applications. And what the storage class describes is a certain set of characteristics. Basically, I want a volume with certain attributes. This could be performance characteristics, reliability characteristics. It could be, for the driver that I'm working on, this storage must be backed by persistent memory. It's things like that. This is all not standardized, but it's basically part of a documentation for the cluster. These storage classes exist and they have this meaning. And that's orthogonal, in my opinion, to storage pools. So the cluster administrator and the application developer, they agree on the storage classes, what the names mean. And the applications, then the stateful set says, I want this disk to be fast. I want it to be on an SSD. This volume can be slow, but higher because I just need it for I don't know, streaming media or something that can be on a hard disk. So you basically agree with your cluster admin to create two different storage classes, and the storage system then picks suitable storage for those different volumes where they are available. And that's where the storage pool comes in. It's basically depends on the cluster setup where that storage is available. It might be on one node where you have fast SSDs, on another node you have larger capacity hard disks, and that means that indirectly through the storage class, your pod ends up running on one node and might not be runnable on another node. But that's basically what Kubernetes needs to figure out.
Right. And also it's possible that the same storage class, like I think I'm just reiterating your point that same storage class then can provision from multiple storage pools because multiple storage pools might match what it wants. And in that case, when the Kubernetes scheduler is deciding placement, it needs to say for this storage class, these are all the storage pools that match it. And these are all the nodes and collection of nodes where all of these matching storage pools can be found, and hence this is the collection of nodes that's allowed set for placement of the pod.
Exactly.
Okay. Yeah. Then I think
And
we are on the same page about this. I just confused in that case.
yeah. So the situation would be, for example, it could be that a storage pool is not suitable for a certain storage class. Say the pool is about hard disks and the storage class explicitly selects SSDs, then there simply wouldn't be an entry for that storage class in that particular storage pool because the capacity would be 0. It wouldn't make sense to have such an entry, and therefore it wouldn't be listed. And then when Kubernetes scheduler looks for storage with topology and a certain class, it just won't find it in that one node that doesn't have an SSD.
Right. So while we are on the subject of influencing the Kubernetes placement, the pod placement, would it also make sense at that time to look at total available capacity on the needed for the needed storage class for every node and take that into account while deciding pod placement? I'm not sure if storage is one of the things that it takes into account while saying this is the best node for this pod.
No, it doesn't. It currently doesn't prioritize. Right now, it doesn't do anything with storage because it has no information about that.
Yeah.
What we currently can do is that the scheduler picks a node for late binding volumes, then asks the storage provisioner to create a volume. The storage provisioner can say, or can try that. It can fail, and it can report back that it can't do that with a currently selected node. And then the kube scheduler tries again with a different node.
Yeah, but that's not the best
No,
approach.
and there's no guarantee that it actually makes a different choice. It doesn't have any state information. It doesn't know, the state might not have changed at all.
Okay.
Unless there is some randomness. It may just end up on the same node again, and that's where the capacity information comes in, because the check then, when looking at candidates for the next node that it tries with, it then can check the size of the current volume against the capacity.
Mm-hmm.
And that will rule out nodes that don't have enough capacity.
Correct. And so there's two pieces, right? One, rule out stuff that doesn't even have capacity. The other is then order them by the freest capacity so that you get some balanced placement.
That would be ideal. It's a separate code. I prefer to not implement it immediately for alpha in 1.19 just to keep the problem simple, but it's doable. There is another hook in the scheduler for prioritizing nodes.
Mm-hmm.
And then we could influence that decision also by available capacities such that we get even spreading across the nodes and try to avoid those where storage is already running low. That's also particularly important when we consider scheduling multiple pods one after the other.
Yes.
If we do that on the node that has most available storage, we limit the effect that outdated data has, because one of the problems here in this proposal really is that this capacity information in the API server only gets updated occasionally. It might get triggered by volume creation because that clearly changes capacity, but that's still there's a delay.
Yes.
So the pod scheduler may end up scheduling multiple pods, and it doesn't try to model what the effect is of scheduling and creating volumes. It just takes whatever information it currently has, and it keeps using that, even though it has already scheduled something that will change the situation. It just doesn't know how the situation will change. So
we are
we have
also doing a POC for this piece ourselves, but yeah, it's in a POC state. I don't have much to say, but I completely appreciate all the problems you're bringing up, because those are the same ones we are facing right now.
Yeah. So this is my main concern. If we have a model where a storage pool can be shared by multiple storage classes, because it sort of exacerbates the problem that the capacity information we use is going to be out of date.
Well, it doesn't change anything.
Yeah,
even if we didn't share it, the problem occurs at the very moment that we have multiple pods that end up using this storage pool, whether it's through the same storage class or through multiple different storage classes. In both cases, we really don't know what the effect is.
Yeah.
So then I guess my question is if the behavior is actually the same in both cases, what value do we get from having this modeled in this way?
Sorry, go ahead.
Yeah. So from a practical perspective, one advantage is that by guessing, I just try to understand how the access patterns will be, that this approach is a bit more compact. So there will be one writer which creates CSI storage pools, or the CSI storage pool object, and then updates that status. And by keeping common information shared, like in particular the node topology, which can be fairly large, we only store that once. We keep the number of total objects smaller compared to this API here. I've switched tabs to basically my comment from 9 days ago, where the alternative is to do not have a storage pool object at the root and just have a storage capacity. I omitted spec and status here, but this is basically the information that will be repeated in every single object. The topology, storage class name, and capacity, that's flattening the structure, but it basically means that we create and need to update a lot more objects.
I'm not really concerned from like the performance aspects of updating objects. What I'm concerned about is from the consumer side of the view. Like if we're gonna consume both models the same way, like what is the benefit from the consumption side that we get?
I think the same argument applies on the consumption side. The consumer still needs to iterate over all that data, and it also needs to read all of them or watch them. So if we update 10 objects at once, it will get 10 updates instead of one where a larger embedded structure gets updated. And iterating is in fact easier and with a more complex structure, because the node topology, which it needs to check, is only represented once. So even the data that it gets is more closely aligned with the checks with usage than splitting it into individual objects.
I mean, putting aside concerns about like number of updates and stuff of the API machinery, what I'm asking is from like a use case perspective, what additional information are we getting from this and how can we use it? How can we benefit from it?
Can I say something? Can I try and answer this from
sure.
maybe my perspective? Okay. So if we don't do end-to-end mapping of storage pools to storage classes, there's lots of functionality that we lose actually. So I'll try and explain from my perspective what is the functional loss. If we cannot map the same storage class to multiple storage pools, then things like stateful sets don't work, because stateful set needs to say, I want my PV on this storage class, but then it needs to have the flexibility of consuming storage pools that might be only accessible on certain nodes as the pods get created. That's one. If we don't have the other way functionality of having each storage pool mapped to multiple storage classes, then the functional loss is, if I want to say, I want to create this PV with 100 IOPS on storage pool SP1, and I want this PV with 10 IOPS on storage pool SP1, I don't have a way to express that because I need two storage classes, one that says IOPS 100, IOPS 10, and both need to map to SP1 so that they both can consume that storage pool. And how the IOPS are implemented is a CSI or lower layer problem, but that's the functional loss from user perspective if we don't have M2M.
Manchi, can we
Okay,
jump
so I
into
think
the use case a little bit more? I want to make sure I understand it.
Sure.
So when you say you have, I guess, storage pool 1 and storage pool 2, both can provision two types of disk, 100 IOPS and 10 IOPS. The effective difference between the two pools is that they belong on different nodes.
Yes.
So you have node 1 that has some pool that can provision two types of disk and node 2 that can provision two types of disks. The types of disks that they can provision are the same, but their accessibility or topology is different. Is that right?
Absolutely.
And so then your concern is that if you have a one-to-one mapping between storage pool to storage class, you're concerned about the explosion of storage classes.
Explosion of storage classes is, like Michelle says, it's just a performance problem. I have a functional problem that I can't express through a PVC template that I want this kind of placement. I have to use different storage classes for the PVC that will be placed on node 1 and a different one for PVC that is placed on node 2, which doesn't allow me to do stateful sets.
That's not my understanding. So I actually discussed this exact use case with Michelle beforehand because I was of the same opinion as you before. And after a long debate, she convinced me otherwise. And so I think my understanding is that you can still express that you want kind of, essentially what you're saying with a storage pool is that you have certain accessibility constraints, right? You're saying that a specific pod has to go to a specific node.
Mm-hmm.
And so what you can do is still say, I have a storage class that has 100 IOPS, but you can also specify topology constraints in your pod to say that you want that workload also to be scheduled to node A, effectively saying you want storage pool 1. And
But what will I say as my storage class? Let's make it a little bit concrete. Let's say that a storage class, in your example, storage class SC 100, and SC 100 maps to a disk that gives me 100 ops.
Yes, so I want to clarify this storage class SC1, say it offers 100 IOPS and it's not tied to one specific node. So it basically represents all pools that you have on every node that can service 100 IOPS.
Okay.
Yeah.
So there is one storage class to many storage pool mapping that you guys are saying is okay.
I think that we might have a misunderstanding about what a pool is. So in this proposal, a pool is inside the nodes. And what Michelle just described is all of the disks across all nodes are one pool. Did I capture that correctly? I think it's
it's a different level of terminology.
Yeah.
So pool in this case is specific to a specific topology, but what I'm talking about is a representation of multiple pools across that all have the same characteristic across all the topologies.
Okay, so we may have a definition problem then what a pool is.
Yeah.
For this proposal here, it is clearly meant that the pool is where the data is. So a cluster with local disks has more than one pool. basically the disks inside the node, maybe one pool. Depends a bit whether that's an LVM, how LVM is set up, for example. We might even have more than one pool per node if you really deal with separate disks. Each disk by itself is managed separately by the CSI driver. That also might be possible. And I think it's that example that is driving the storage pool cap from VMware, where they explicitly want to have some way of selecting sub-node pools to achieve certain, or to get certain constraints satisfied, like my two volumes must not be on the same disk.
Yeah.
Yeah, so that's
Yes, so for that use case, what I would want to recommend is each of those collections of pools be a separate storage class.
We can
So
always
say like one collection of pools can be hard drives, another collection of pools can be SSDs, and we can map that to storage class to say have one storage class represents SSDs and one storage class represents hard drives.
Yeah, so let's take a step back. I think you hit the nail on the head by saying the definition of storage pool is what is confusing. So let's stop using the word storage pool and let's start being more specific about what are the things that the specific attributes that we care about. So the ones that I've heard about are 2 or 3 main things. One is capacity. The pool has some inherent capacity, limited capacity, and we want to make the Kubernetes scheduler aware of this limitation when it's doing scheduling. The second is accessibility constraints. The volume that is provisioned may not be equally accessible to all the nodes, so we want to make the Kubernetes scheduler aware of this constraint and be able to influence it from your workload. And so those are the 2 main kind of use cases that I've seen so far for a storage pool. Is there any other? Because those 2 existing storage pools, I think those 2 existing functionalities, topology and capacity, can be met by having just storage classes and not a standalone storage pool object.
Another thing that we may add in the future is the health of the pool.
Volume health.
Not one, but it's like the pool, more like the pool health, right? Could be like the disk is failing, so you don't really want to schedule on that disk. That's another thing that we can add in the future, maybe.
The one thing, like from use case perspective, we'll like to achieve one way or the other is the ability to represent every disk attached to a node as a pool and make in the CSI driver or wherever, make some intelligent placement decisions about where a PV should be placed on the different disks. Like, let's take out storage pool entirely. Let me just say it as the raw hardware topology. I would like to be able to pick a single disk and say, I want my PVC to go to this disk.
So it sounds like what you're trying to do, and correct me if I'm wrong, you want to kind of circumvent the Kubernetes scheduler. Then you as an end user want the kind of raw hardware layout exposed directly to your application. So from your application, you can kind of select and manipulate it. Is that correct?
Potentially. Correct, yes. Like for example, if there is like an operator of an object store running and it can say that I want to put 4 different stripes of my erasure coding on these 4 different disks attached to this node. And there could be 2 kinds of disks attached. One is NVMe and one is hard drives. And I want to be able to say, I want to go to the hard drives and I want my 4 stripes to be on 4 different.
So this use case that you're saying now is different from what you just said, right? Right now, what you're talking about is kind of attributes of different types of classes, essentially, of disks.
Yes,
so
but I should not confuse it. Let's just focus on the fact that there are 4 disks, and I would like to somehow be able to say, if possible, I would like to go to a certain disk.
Right, and it's independent of kind of a characteristic of any one of those disks. You're kind of, this is not something that's already represented in Kubernetes because it's not.
It's like a failure domain.
Yes.
Right.
Yes. I think that's a very good way to express. It's probably a storage pool to me in my head. One thing it is a failure domain, but it also has characteristics like, is it fast? Is it slow storage? Is it what? So it's a failure domain with some storage characteristics to it.
Okay, so that helps. So failure domain.
And there's an
Hey,
accessibility
excuse me,
domain.
can I share some of the diagram from Christian's cup? I think that actually shows what we want to achieve, the use case.
Sure,
Maybe that, yeah.
I'll just
Yeah, can I?
sharing,
Yeah, so I think
and
that maybe
you can take over.
picture, I think it's looking at picture maybe easier than just talking about it. So there are two use cases here, right? So this is the one, this one that I think Mansi has been talking about, right? So you can have 3 replicas, and then each one has 4 PVCs, and we want them to be scheduled across 4 different disks on that node. So we want to be able to say, we want to pick a pool, but we want those PVCs to be scheduled not on the same pool on this node. So something like that. So so it's like a more finer granularity to specify the affinity, anti-affinity rule. So it's more than what we have today.
Okay, so this,
yeah.
Okay, sorry, go ahead.
Yeah, this one, and then there was another one. So this one is more like what we have been talking about, but then there's also in this one, right? So it's this is similar, but it's a little different, right? So also, I say I want this pod to have this 2 volumes, but we want them to be on different storage pods, so storage pools. So yeah, so there's two diagrams.
Got it. And so the use case is kind of, you have an application. If you provision naively, it may be that you end up getting all your volumes provisioned on disk 1.
Yeah.
Which would be bad because the failure domain is all on a single disk. If that disk fails, you've failed everything. So ideally for that application, you want to spread your volumes intelligently across all 4. All 4 pools. Okay, so that helps.
Is it possible in this example to say have disk 1 be a storage class, disk 2 be a storage class, disk 3 be a storage class, and disk 4 be a storage class? So then, and your stateful set, you have 4 PVCs pointing to 4 storage classes.
We can't do, because they are all of the same type of disks actually. So they belong to the same storage class. If you talk about like a storage class represent a certain service level, then they are all
not sure
the same.
Storage class currently really represents that today, right? The definition of storage class is very open-ended right now.
So Michelle, are you saying that the disk 1 of all nodes maps to one storage class, and disk 2 of all nodes maps to another storage class?
Correct.
Interesting.
So that wouldn't work because which node you're on matters. Like on some nodes, disk 1 is full, and on other nodes, disk 1 is empty. And so the scheduler needs to know which node you're talking about.
And another thing is if we want to support both required and preferred, right? So if you're only saying strictly they are not together, maybe it's okay to have 4
I think we should
classes.
explain required and preferred a little bit.
I guess so one interesting extension of this use case is so in this case, like all the disks are on a node, but there are storage systems that have topology
like
independent of the nodes. So, and even there you would want to spread.
Right,
today,
so like this one. Yeah,
topology, today topology in Kubernetes is always relative to a node, a Kubernetes node. we don't have a way to support topology outside of a Kubernetes cluster. So I'm wondering, like, if we want to address, like, both use cases sort of have this this use case of I want to spread across failure domains. I'm just wondering if maybe we would need to consider some other way of addressing that use case.
Yeah, and I think we started this discussion in the volume group KEP. I think one of the goals we were hoping for there was the ability to spread across failure domains. And the details of how that would be done has not been thought out yet.
Yeah, so that one, well, I know we just started that one. That one is
Yeah.
kind of built upon sorting pool concept because the group itself does not have capacity. So that's a problem if you say, talk about groups. So I think, so how to
I guess one thing is like
into that.
the storage system itself understands how the disks are laid out and how much capacity is available. Is it possible that we sort of try to simplify this for the user and say, hey, the storage system understands exactly how it's laid out. If you tell the storage system that you want some group of volumes to be spread across different failure domains, if that's all we told the storage system, could the storage system figure it out themselves how to spread and allocate the disks?
Not sure how that would work.
Yeah.
But
taking
yeah,
a step back, I agree with Michelle's approach here, which is what we don't want to do is kind of expose arbitrary knobs to the user, right? If we expose 100 knobs, effectively the API becomes useless. What we want to do is kind of make automatic intelligent decisions on behalf of the user, with them kind of just giving the bare minimum of input that we absolutely need from them. Exposing some kind of hole all the way from the bottom out to the user is a hack because we couldn't come up with a better API. The ideal solution I would want here is some automated mechanism for either the Kubernetes scheduler or the storage system via the CSI driver to be able to do the intelligent placement and spread across failure domains. And so the question is, should the Kubernetes scheduler do the assignments there, or should the storage system do the assignment? I think Michelle's argument here is that if you let the storage system do it, the storage system already knows about the internal failure domains. The only additional information it needs is kind of workload information about like these pods are related to each other, please spread them. Versus the alternative, which is making the Kubernetes scheduler understand the internal topology requirements of a specific storage system and do that in a generic way that would work for all storage systems.
My understanding of the storage placement cap actually was that this decision of where to place storage is supposed to be done by an operator. So it wasn't, I think, not the initial goal to actually enhance Kubernetes itself to make more intelligent decisions. It always has been the goal that we just find a way to expose information.
So I want to push back on that. I've heard that a lot and I don't understand it. Why do we want to expose this up beyond Kubernetes? Why is it essentially what we're saying the consumer or user of Kubernetes problem to figure out kind of underlying storage placement? Why?
Because there are these really sophisticated storage systems like vSAN, for example. I know you guys don't like to take that example, but let's say vSAN or object store like MinIO that has lot of capabilities in terms of making intelligent storage placements. And today the Kubernetes model doesn't expose enough about the hardware topology to these systems to be able to do this in bare metal environments. So they are going very blind, and it works wonderfully well on AWS or GKE, because there you do three-way replication of storage underneath and you expect them to stay blind. But on bare metal, that same analogy doesn't work. They don't have anything to work with to really understand the storage layout underneath to make those better decisions. And we have an explosion of these intelligent storage systems there. There's Cassandra, there is Mongo, there is object stores, there is Cockroach. All of them want to see this, but there is nothing that helps them. That's at least my
So I agree that storage failure domains are not currently handled within the Kubernetes ecosystem. I guess my question is more around why are we focused on kind of bypassing Kubernetes and making this the problem of a Kubernetes user to solve? Why are we not trying to solve it within Kubernetes?
We are trying to solve this within Kubernetes, right? That's why we are having this CAF.
No, but I'm just pushing back on the point of like, hey, let's have operators and just expose kind of raw storage topology information up to an operator, and the operator will figure it out. That seems like what we're doing is basically poking a hole all the way through the Kubernetes API down to the storage system and saying, well, forget the CSI driver, forget Kubernetes and Kubernetes scheduler. Somebody who's using Kubernetes will figure out what to do. And so, that seems like the wrong approach to me.
Are you saying I want to understand why the operator should have a capability of expressing what it wants to do, and somehow something in Kubernetes should translate that into actual placement?
Right. The whole point of kind of
I want to add to that. I just was trying to clarify.
Sure.
So if you do that though, the operator cannot express a wish without understanding what's available underneath. Do I have 5 disks? Do I have 3 disks per node? Do I have NVMEs and hard drives, or I have only hard drives? Do I have, nodes it does know, but just like that, what is then at the storage layer, what is available? Unless it knows what's available, what's healthy, which one of those has capacity, unless it has that information, it cannot even express a wish.
Right. So what we want ultimately is they should be able to express the minimum required information, right? Ideally, it's something like, hey, please spread across all failure domains. And if they say that, we intelligently figure out what these failure domains are on the storage system and take that into account when we are scheduling and provisioning disks. Right.
But that's like saying create a stateful set without telling them how many nodes you have on the cluster.
Which is exactly what your stateful set does today. All right. It doesn't care how many nodes are on your cluster. Your stateful set doesn't say, hey, please tell me exactly where to schedule every single instance. Kubernetes figures it out for you. That's kind of the whole point.
If I may interject here, I see both sides as something that has merit. The problem that I see is that by saying this has to be solved in Kubernetes, we are basically tackling a problem that just may not have a good solution in Kubernetes unless we first do something else, something simpler that is specific to one application, and then later on generalize it so that it becomes a built-in feature of Kubernetes. So I see this advanced storage placement cap as a first starting point that enables experiments by agreeing on a certain API. And if that turns into something in say in one operator, I know, Saad, you don't like that term, but operator basically now is the out of tree component where such an experiment with automatic placement can be done. And if that leads to some new ideas that then can be added to Kubernetes, I don't see why that shouldn't happen. I just wouldn't make it a requirement.
So I think
just my 2 cents.
My kind of point around all of this is that the purpose of Kubernetes storage is to act as a abstraction layer that enables kind of workload portability. So the things that you deploy on top of Kubernetes, the workloads should be able to operate independent of the underlying storage system. We want to balance that with the ability to ensure that all the functionality that any given storage system has is exposed and available for use. And that's why we have those opaque parameters on storage class that allow you to kind of customize your storage system as you wish. My kind of ultimate fear is that we expose, raw underlying storage implementations, and workloads start becoming dependent on those, and that effectively removes the workload portability. So whenever we start talking, or the kind of conversation starts heading towards, let's poke a hole in the API and start from there, it makes me take a step back and say, okay, what are the actual use cases that we're trying to solve? Let's come up with generic APIs within Kubernetes, understand who the consumers are. Is it the Kubernetes scheduler? Is it the CSI drivers? Let's focus on that instead of, and figure out the kind of minimal things that we need to expose between the storage system and that consumer, rather than just poking a big hole and saying, well, let's just expose all the information up to the end user and somebody will figure it out, right?
So I think storage pool is pretty general concept. Like every storage system has that concept.
Right. Just
The
because the storage pool is a general concept that a storage system has doesn't mean that the raw concept of a storage pool must be exposed up to a user of application developer using Kubernetes, right?
Right. So yeah, if there
what
are
we want
like
to focus
use
on
right.
is kind of the use cases. And the use case that I heard today that really struck with me is storage failure domain spreading. And I agree, that's kind of something that we've punted on for a while. So let's double down on that and say, okay, where do we want, first we have to figure out who the consumer is of this information. We know that the information is locked away in the storage system today, and only the storage system is aware of it. So we kind of have three options here. One, we can say, let's give the storage system more information so that it can effectively make a decision. The second option is give Kubernetes enough information about the storage system so that Kubernetes scheduler can make the most optimal decision. The third thing that I'm hearing on this call is just poke it all the way up through the Kubernetes API, surface that information to a consumer of Kubernetes and let the consumer figure it out. And so I just want to push back on that last option and say that's not the path we should go down. Let's focus on either number one or number two.
I don't think we are pushing this to the consumer though. Consumer is basically the user will only specify at a very high level.
And that would be perfect. That's exactly what I would want. Like at a very high level, the consumer says, I want, spreading or kind of some policy for spreading, but not I think that's what we trying to propose. And maybe there's some misunderstanding, but okay,
what do we want to so this is my understanding. What we're trying to propose is like the user will be able to say, okay, in the stateful set, I want those PVs to be scheduled on those pools, but I don't want them to be scheduled on the same storage pool, something like that. So it's like the affinity or anti-affinity rule, not more than that.
That's perfectly fine, as long as we don't kind of hard code like the concept of like, for example, what I wanted to avoid when we did topology was every single kind of cluster that you're going to have is going to have a different cluster topology depending on how you've deployed it. If you're on cloud, you'll have regions and zones. If you're on-prem, you might have racks or even some other custom topology. And the initial approaches that folks wanted to take there were kind of hard code those concepts into the API. And so similarly for storage systems, we want to come up with some way to be able to express that there are failure domains within the storage system and give that information to whoever needs it to make the decision. So I think what you're saying, Xing, is that you're okay with letting the Kubernetes system make an intelligent decision based off of failure domains. And I think that's a perfectly fine approach to explore. So let's explore that if
okay.
you all agree.
Yeah, we probably need to write down some more detailed cases, how that would work, how you define this and that, and see if we agree on that. Yeah, I think there might be some misunderstanding here.
So we have 5 minutes left. I think with advanced storage placement, that clearly needs further discussion. But what I would like to see is that we at least move forward with the storage capacity tracking one way or another. Personally, I would prefer to keep the API as proposed, as in the document, with this root CSI storage pool. It feels appropriate for this case. Whether we then expand its usage to things like advanced placement, that can be seen later on. But I think it's a good starting point for the API and for what we need to implement for the capacity side of things.
So I think the pushback here has been that the use cases that we've been focused on so far, capacity and topology, accessibility topology, could both be satisfied without having a standalone storage pool object. And kind of the principle that we start with is don't add unnecessary API, right? Like just because we think something might be hypothetically needed in the future, let's not add it until we need it. So if we think that storage pool is a requirement, let's come up with a concrete use case for it. It sounds like storage failure domain spreading might be a good use case for it, but we haven't fleshed it out. So I would hesitate to say, let's add it and then figure out the use case later. If we think that it's important, let's kind of flesh it out.
So what is then the API that you want to see in 119? Is it the alternative that I proposed where we replicate the information across multiple objects? Or is it the name itself for what's currently called CSI storage pool?
So I think for just the capacity and accessible topology use cases, a one-to-one mapping between a storage class and the storage pool is what I'm looking for. Whether that storage pool is a standalone object, whether you call that storage pool a storage class capacity, all of that is implementation detail to me. But I think the thing that makes most sense to me based on those two use cases is strict one-to-one mapping.
Yeah, so
Anything beyond that, I think I have concerns with.
Yeah, so I'm just a little worried that if we go that route, then it may limit our ability to get this to work for storage pool at all in the future. So I think we still need to think about how it works.
Yeah, it closes our doors completely at that point.
And so I think we need to explore that. I don't want to do is paint us into a corner. If we think this is an important use case, let's talk through it and figure it out.
My concern here is that if it's just, it basically says, keep the API simple, but if we later on find out that we need something more complex, it basically means rewriting the whole thing, doing a major API break. I understand, but we don't know yet whether this API that I have in the cap is the right one, but it works for the proposed purpose and it might actually be more efficient. That's my feeling. So why not use it?
I mean, I would be okay with that. So if we want to go to alpha with a one-to-one storage mapping, let's do it. It'll, less is more.
Okay.
I think we do need to think about
my proposal actually was to keep the more complex structure because it's actually, I think, easier to implement, more efficient, and later on figure out whether it has additional usages. It's not wrong per se for just the use cases that were outlined here in the cap, in my cap.
And sorry, you were proposing many to many?
I'm proposing basically just, well, basically it's many to many. A pool is local to a node, may have multiple classes. There might also be the opposite direction. I'm slicing that end-to-end mapping by saying I'm starting with a pool and adding information per class. So it's basically, in that sense, it's one pool and all the storage classes that apply to it. That's how I'm representing it. That doesn't mean that the storage classes only is in the list for one pool. It may appear in multiple pool objects, and in fact it will, because certain simple storage classes like my PMAM example, that's just one storage class that just says I want PMAM. That will then have multiple storage pools where it has different capacity values. But the API basically slices it. It's using the CSI storage pool as a starting point. It's
Yeah, I have a lot of reservations about that approach. It just seems to me like we think it's going to work for one or two use cases, and we think it might work for another one. We're adding a lot of API. It doesn't seem like a good approach to me.
Okay, I see my arguments are not convincing enough. In that case, the only way I see forward is to flatten the whole thing. I had a tentative proposal for that revised API in that comment that I showed earlier. And if Saad and Michelle say that this is what they'll accept, I'll just rewrite the cap with
But
that.
I would have concerns with that approach though.
Yeah, and then I have other people saying no, that doesn't work either. So how?
Because
I appreciate, you're in a really hard spot, Patrick. I really appreciate that. I'm sorry. I don't think any of us is trying to be a jerk here. I think we're all trying to make sure that we're making something that'll work best for end users. And I know this is frustrating, so I apologize. I hate to suggest it, but can we do another meeting to see if we can come to a consensus rather than try to make a decision in the last minute? I need to jump off in another meeting.
We can do another meeting. I just don't see that we'll come to
so
a conclusion
let's look at the let's look at the strategy pool concept just to see how we can.
Yeah, I'm so sorry. I really need to jump off.
Okay, all right.
meeting.
Thank you. Okay, sorry. So let's schedule another meeting.
Sounds
sorry,
good.
Patrick. Thank you.
Thank you. Thank you, everyone.
Bye.
Bye.
Bye.